Okay, this is a continuation of Chapter 18. It's going to be your second part. We're going to talk about a bunch of different things that relate to standard conditions and more delta G and more entropy, and just kind of expand upon what we've already done. So if you'll recall, standard conditions basically just mean, just like what it says, it's a standard condition. It's a condition in which things are just normal. So what that means is, for gas, we're talking about a pressure of 1 atm, 25 degrees Celsius, typically 1 molar. And that's true for pretty much everything. So once we have these standard state conditions, it just means, kind of, if you remember from Gen Chem 1 when we talked about ideal gas laws, we talked about gases behaving ideally, and all those problems when we used PV equals nRT, it would have to say somewhere in the problem that it was gases behaving ideally or at STP, standard temperature and pressure, etc. So all that really meant was nothing was in the extreme. That's all we're using for standard state conditions when we talk about entropy and enthalpy here as well. So we talked about the first law of thermodynamics, which is just basically enthalpy. We talked about the second law, which was the entropy, matter of chaos. So now our third law of thermo is just the idea of entropy being absolute entropy. So by definition, the amount of the substance that it contains its energy and how that energy is dispersed, and basically what's going to happen because of the energy it has within its particles and its structure and all that. So the takeaway here, let me get my pen going. The takeaway here is this right here. Okay. A perfect crystal at absolute zero, remember this is why we convert with Kelvin, the 273.15, that's how we use it, because of absolute zero. If we have a perfect crystal at absolute zero, the absolute entropy is 0 joules per mole Kelvin. So worry less about mathematics behind this, worry more about conceptual. So when we talk about this absolute entropy, we need to talk about it again in terms of delta S of the system being positive and negative, and how we can relate delta S of the system, reaction, and of course then universe. So again, when delta S of the system is positive, we have a favorable entropy change, meaning we're becoming more chaotic. Basically, it might be something like going from a solid to a liquid or a liquid to a gas. We're becoming more disorganized with a positive delta S of the system. So when delta S is negative, entropy is not favored. It is not a favorable reaction. So it can't be spontaneous. And if you remember, when you're talking about spontaneity, you're talking about it being an irreversible reaction. So the examples we gave last time were, a car rusting or a waterfall traveling up the hill instead of down the hill, right? Those are irreversible reactions. You can't get the rust back into metal, and you can't get a waterfall to go up a hill or up a cliff, whatever. So when we relate our system and our reaction, if you remember from Gen Chem 1, we had Q of the system was equal to negative Q of the reaction. It's very similar in this case with entropy and delta S. So we can say that delta S of the system is equal to delta S of the reaction. In this case, not the negative of it, because remember, we're talking about spontaneity and if it's irreversible or not. And we're simply just going to say the S naught of the products minus the S naught of the reactants. Now, these are values that would either be given to you or you'd have to look up on a chart. You're never expected to memorize them. Think of it like H naught. When we had bonds breaking and bonds forming, we looked up those values on a chart and did the products minus the reactants. So when you see this knot, this subscript 0 looking thing, looks like a degree symbol. We call it a knot. It's not like degrees Celsius or degrees Fahrenheit, but in this case it's an S knot. That is telling you that we are in standard state conditions. when we're in standard state conditions, that's that 25 degrees Celsius, 1 atm for pressure, 1 molar. Okay, those are our standard state conditions. So, for example, again, we said that these are constants, and every different compound or element, whether it's in its elemental state, a compound, they all have their own individual S naught, just like every compound or element has its own individual density, but it's a constant that doesn't change. One of the things you really need to be paying attention to when you're doing the math behind this is you have to pay attention to their states. So, for example, liquid water is 70 joules per mole Kelvin, where gaseous water or steam is 188.8 joules per mole Kelvin. Here's just some examples. Again, you can look these up. For test purposes, I will just probably build them into the question. But when you're doing your mini quizzes, it's just expected that you're going to look up these values. And if you look here, you'll notice these are just a few of the very most common ones that you will see. When you look here, you can see, all these gaseous states have pretty high, S naughts, where the solids are significantly lower. That should tell you something about the entropy and how increasing entropy increases the value of, the numerical value that we're using here. So it should make sense if entropy is the point of increasing chaos, that a solid would have a much lower value than, say, for example, a gas. And it doesn't even matter that we're looking at things that are completely different. Like, for example, solid iron here and gaseous argon there. It doesn't matter that they're different. What makes them so dramatically different in their S naughts is the fact that one is a solid and one is a gas. There's just an incredible more amount of energy in the gaseous phase than in the solid phase. So again, when you talk about molar mass, we can look at that to see what would have, a larger entropy. So your one rule of thumb right here, the larger the mass, the larger the entropy. Again, that should make sense. Because if we're talking about taking an individual element and taking it from all through the phases, from a solid to a liquid to a gas, yes, we know that the gas is going to have higher entropy. However, it should also make sense that the bigger it is, the more entropy or chaos will be present, simply because it's just bigger. All right, so the less constrained the structure, the larger the entropy. So what do we mean by that? The less constrained the structure. Well, when we talk about constraint, and you're going to do a lot of this, in fact, this is going to be one of your bases, in organic chemistry. So you're going to find that structure plays an enormous role in how these compounds and molecules are going to behave. So if we compare a diamond to graphite, remember graphite, like what we write with our pencil with, where diamond is the much more organized carbon that's been converted to pretty sparkly, beautiful jewelry that we know and love, right? If you look at the structures of these, the diamond format, it's very, literally, I don't mean to be repetitive, but it's very structured, it's very rigid, it's very repeating geometric patterns, where the graphite is more random, okay? It's not as rigid in its structure. So because there's less constraint with the graphite and the more, we'll say, loosely repeating patterns, it's going to have a higher entropy. Okay, so again, the larger it is, the more entropy, the less rigid in its structure, the more entropy. And so if we look and compare, for example, argon and nitrogen monoxide, you can see that they're relatively similar in molar masses, where argon is slightly larger. And we are talking about both of these in the gaseous phases. So you might say, well, if argon is slightly larger, why does it have a smaller S naught, smaller entropy value? And the long and short is chaos, right? We do have a smaller molar mass for nitrogen monoxide. However, there's a less rigid structuring of it, And because there's two different molecules there as opposed to just pure argon, the energy can disperse more readily. All right. Now, this is also something that's going to be very, very, you're going to hit heavy in when you go on to organic. So we have all sorts of different types of motion or movements that these molecules can do. So we just said in the previous slide, well, what do we mean it can disperse the energy, more readily if there's two things there as opposed to one? The answer are these three things right here: transitional, rotational, and vibrational motion. So what does that mean? That simply means exactly like what it sounds. We can have motion that transfers energy. We can have energy that is rotating. And think of if I hold, it's hard to, I'm trying to think of a good example. So if I'm holding the end of a stick, with both hands, and I could kind of twist one hand clockwise and the other, counterclockwise, that's what that rotational motion is. And then vibrational motion, again, just like what it sounds. The energy being dispersed or energy being transferred by way of the molecules vibrating. So this transitional, rotational, and vibrational motion, you're going to get into really, really hard when you go on to organic next semester. So you just need, for my class, you need to understand this conceptually. You'll get way more into it in Organic 1. So when we talk about the standard entropy change and delta S not reaction, again, it's just simply the values we're going to look up on a chart or be given of the products minus the reactants. And you can't ever forget to include any coefficients that are in front of whatever the compound is. So if I had 2NO yields N2O2, for example, I'm totally making this up. Whatever value I would have for NO, that's going to be my reactant. Whatever value I have for N2O2, that's going to be my product. So I would take the value of N2O2 and subtract it from 2 times the value of NO, because I'm taking into account that coefficient from the balanced chemical reaction. So if we look at an example here, calculate the delta S reaction for this balanced chemical equation. Here's the balanced chemical equation. They've already balanced it for you. Keep in mind, always check when you take a test with me, because I don't always balance it for you. So first things you'd have to do are look up or be given in an appendix or within the problem the S naughts of each product and reactant. So you have the products, which you can see from right here. Sorry, I'm trying to, it's a little small spot there. We're going to say 4 times the value of the nitrogen monoxide. So right here, plus 6 times the value of the water. And again, this 4 and this 6 are coming from the balanced chemical reaction. And I would just simply add them together as my products and subtract from it 4 times the S naught value of NH3, right there, plus the 5 times the S naught value of O2, right here. Now, remember, when you're looking this up, if you're looking in the back of your book in Appendix 2B, you have to make sure you're paying attention to the states. Don't forget to pay attention to the states, because the values of the gas, liquid, and solid are going to change with, whatever your compound is. Once you have all those numbers plugged and chugged, you literally are just going to multiply them and add them together to get your final delta S of this reaction. Pretty straightforward. Go ahead and do practice this one. You can find the values in the back of your book in Appendix 2B. If you have the e-text, you can just drop down to your list of chapters and it should take you right to Appendix 2B. But just look these values up and you're simply going to do the products minus the reactants. Don't forget to multiply by their moles that are from the balanced chemical equation, where N is moles. and that's going to be delta S naught of the reaction. So now we're going to kind of summarize a lot of things. Okay, we've talked about delta S ad nauseum at this point. Now we're going to jump back to delta G. So far what we've talked about in this chapter is that delta G of the reaction, remember, you'll see that G naught there, that's going to tell you standard state conditions. So that's why we have this 25 degrees Celsius here. So we have that delta G naught of the reaction is equal to the delta G of the products minus the the G of the reactants. Again, these are, you get these right from a chart. You don't have to memorize them. And then at temperatures anywhere other than 25 degrees Celsius, because that's not standard state conditions, we need to go ahead and use this reaction, which relates our delta H minus the temperature and the delta S of the reaction. Don't forget to convert your temperature to Kelvin. All right. Now, the other thing we can do, if you remember back from Gen Chem 1, Hess's law, where if you remember, we had a multi-step reaction that was stepwise. And so each step had a varying amount of H, and we had to find it overall for the whole entire reaction. All we simply did was add together all the H's once we had everything flipped and multiplied appropriately. Well, the same can apply with delta G. So if I have delta G of a total, all that's going to be is the delta G of the first reaction plus a second reaction plus the third reaction, et cetera, et cetera. So again, it's literally taking the individual delta G of each individual reaction and then adding them all together. But we're going to use products minus reactants at standard state conditions, which is 25 degrees Celsius. And then at all other temperatures, we're going to need to use this one. The delta G of the reaction is equal to delta H of the reaction minus T delta S of the reaction. Now, if we look at this and we calculate the standard change and Gibbs free energy, what we see here is one possible initial step in the formation of acid rain is the oxidation of the pollutant SO2 to SO3 by the reaction. Here's the reaction for you. Calculate delta G at 25 degrees Celsius. You see that 25 degrees Celsius, and you need to be thinking standard state conditions. Now you might be wondering, well, why are we using this if we know it's at standard state conditions? Well, let's look. So we absolutely can do products minus reactants in this case because it is standard state conditions. So we can just go to our chart and say, okay, products minus reactants, et cetera, plug and chug, do the math. And there it is. However, what if I don't have this information readily available to me? All right, you can see they first solve for delta H naught of the reaction, which is the same as calculating delta G naught, products minus reactants. You should see the theme here of all these products minus reactants. So I can find the delta H, again, right from the chart in the appendix in your book. And then I can go ahead and do the same thing with the delta S naught. Again, products minus reactants. Make sure you're paying very close attention to the fact that delta H is in kilojoules where S naught is in joules. You have to convert one of them. Doesn't matter which one you convert. It's usually easiest to convert the delta H. So once you have, this is step 2, once you have your delta S naught, just simply from products minus reactants, and looking at your chart, then you can just plug and chug into this equation because we now have solved for delta H of the reaction. We solved for delta S of the reaction. The temperature was given in the equation, and we can just convert it to Kelvin and plug and chug. Now, here, this reaction we know is spontaneous because it's a negative delta G. If you remember, negative delta G means that it is spontaneous and therefore irreversible. Okay, here's just another example of doing this. You have for the reaction in 18.5 here, this, where'd 18.5 go? No, 18.5 is gone. Okay, well, go in your book and look at 18.5 for this problem here. I don't know what happened to my slide. It's just gone. Sorry. And do go ahead and work through this, because now you can see we're at 125 degrees Celsius, so not standard state conditions. So we actually do what we're forced to use this equation, as opposed to, you know, just products minus reactants. But you are going to do the products minus reactants here. You're going to solve for that also with here. And then literally you'll just plug and chug once you convert the 125 to Kelvin. Okay. Again, I'm not going to go over this again, but our delta G's of formation simply just mean we're going to go to a chart and look up whatever the delta G is for that particular element of a reaction or compounds. It is true that all pure elements in their standard state is 0. So you'll see like H2, O2, N2. Remember, these are all the diatoms, right? They are in their standard state. They are in their free state, and therefore their delta G is 0. Everything else, you just kind of look up on a chart. I recommend going through these and just practicing to kind of burn it into your brain. The math here is not difficult at all. It's just a matter of recognizing products minus reactants, when I can use it, when I can't use it, etc. Okay, so now let's talk about these delta G relationships. If there are a series of reactions, then again, the sum of the delta G is equal to all the individual delta G's added together. You'll note delta G is a state function. So what does that mean? If you remember from Gen Chem 1, when we had the mountain, here's my beautiful mountain, right? And we had little people at the bottom of the hill that were hiking. Now, some people were going up the really steep side and getting to the top, where other people, if you remember, were doing that winding pathway. Okay? In the end, the reality is all the people got from the bottom of the mountain to the same point at the top of the mountain. It didn't matter the pathway in which they got there. What matters is they just did. Okay? So just recall state function. If a reaction is reversed, the sign of delta G reverses. So if we have an individual reaction where it's a negative delta G and we have to flip that reaction, then we got to make it a positive delta G. If we multiply it by anything, then we have to multiply the delta G by something. Again, it's just like Hess's law. So if we look at this, this should kind of jog your memory if you're forgetting what Hess's law is. When we look at this right here, we can see we have individual reactions that will eventually give us this one overall reaction right here. There's your overall reaction. So we have 3 individual, stepwise, if you will, reactions. So the question is, how do I manipulate these so that in the end, they cancel out, all the intermediates cancel out, and then what's left adds up to the overall reaction, okay? So if I start here and I say, okay, with the very first reaction, I got C3H8 plus 5O2. Those are going to be on my reactant side. But if you'll note in the overall reaction, C3H8 is going to be on the product side. So that means I have to flip this reaction, okay? I can also see that there's no coefficient in front of the propane, the C3H8. So I don't, at this point, I don't really need to multiply it by anything, but I do need to change that sign to positive. So then I look at, reaction number 2. Reaction number 2 has carbon and oxygen on the reactant side, and carbon is on the reactant side of the original. So I don't have to flip anything here, but There's a 3 in front of that carbon. I got nothing in front of this carbon, so I'm going to go ahead and multiply everything by 3. So I'll have a 3 in front of that, a 3 in front of that, and a 3 in front of that. Okay? And then finally, H2 is on the product side, or I'm sorry, the reactant side, and it's on the reactant side in the original. So I don't need to flip anything here either. But there's a 2 in front of that H2 and a 4 in front of this one. So I'm going to have to multiply everything by 2. Okay? Now, if we've done this all correctly, so we've flipped this, changed the sign. We didn't need to flip here. We multiplied by 3, multiplied by 3. And then here, just multiplied by 2. We didn't have to flip anything, but you got to multiply by 2. And in the end, all the intermediates cancel out. Remember, the intermediates are the ones that are formed in one step, used in another. So this CO2 cancels out with this one, so they go bye-bye. These 4 waters cancel out with these 4 waters. We got 3, 4, 5, O2, 1, 2, 3, 4, 5, O2. And so everything that's left should match exactly what the overall reaction was. Once we've ensured we've done it correctly, all you're doing is adding these up to get a total amount. Go ahead and try practice 18.9 and see if you can get it to work for you. All right, so this whole idea of what's quote-unquote free about free energy, we don't mean it's free. It's not like we're paying a bill for it, right? We're just talking about, by definition, the max amount of energy released by a system, right? Gibbs free energy, how much energy is given off. Remember, conservation of energy says, energy can neither be created nor destroyed. It can only change formats. So when a system releases energy out into the surroundings and it's changing its form of energy, the question is, with this free energy given to the surroundings, what is the max amount of each system that it can allow? So this part, this second bullet right here, for many exothermic reactions, some of the heat released as a result of the enthalpy change goes into increasing the entropy of the surroundings. So what all that means is some of that energy or heat that it's given off, it's going to be doing a different job. It's going to be increasing the entropy of the surroundings. Think of in the movies when you have, I don't know, a car on the side of the road and it blows up in front of a building, right? Somebody's put a bomb there or something. And there are times when, the windows will blow out of the building it's next to, and, you can almost see that wave of energy. Well, some of that energy is actually increasing the entropy, while the rest of it is actually doing the work of transforming the energy into something else, going from a chemical energy, for example, to, say, a mechanical energy, okay? Some of the free energy is lost to the surroundings. For example, when you have an exothermic reaction, let's say you mix a very strong acid and base in a test tube, you can feel that test tube getting warm. That's energy that's, we say lost, but I'm going to use that term loosely. Again, energy is neither created nor destroyed. It doesn't poof, go away, and poof, appear magically. So when we say it gets lost to heating up the surroundings, that is a change in its free energy. So here's just another kind of visual of this. If I have carbon, graphite carbon, not diamond carbon, and I add hydrogen gas to it, I'm going to get methane. Okay? When I get that methane, the maximum amount of work that can be done is 50.5 kilojoules. All right? The minimum heat lost, 24.1 kilojoules. So I can look and say, okay, the delta H here is negative, And therefore, we know that means it's exothermic, okay? Exothermic is more favorable. But our delta S, if we did the math, would be negative and therefore unfavorable. However, when we combine the two of our delta H and delta S times whatever temperature this is at, and we find that the overall delta G is negative, that means that overall it is spontaneous. So graphite with hydrogen gas will go ahead and form methane relatively easily. When we have a negative delta G, just because we have one piece of this delta S, that would seem to be unfavorable, that doesn't mean that the overall delta G would not still be spontaneous. It's just a matter of size of the other thing. How large is your delta S? How large is your delta H? Will one overcome mathematically the other to make delta G positive at a given point? So again, we're not going to worry too much about this, except to understand that there is a theoretical limit of the energy, but just depending on the amount of work. And once we hit our quote theoretical limit, it is a reversible reaction. So what you're seeing here in these pictures is you have gas that's pushing up on this platform, okay? And the less sand that's present to weigh it down, so to speak, the higher that platform's going to be able to move. But eventually, if I have zero sand, if I have one little grain of sand on that platform, eventually there's going to be a stopping point for how high that platform can be raised by the gas doing transferring this energy and pushing it up. So non-standard conditions, this is where we have to start using our log functions again. So non-standard conditions mean not normal state, maybe not at 1 atm, maybe not a concentration of 1 molar. When we have non-standard conditions, we're simply going to use this equation. This delta G naught would be what you would solve for during standard conditions. This right here accounts for the change of not being in standard conditions. Your book does go through the derivation of this equation. I don't ever require you to know those. If you'd like to go through it for your own fun, by all means, go through it. But this delta G naught is what we would solve for in standard conditions. R is our ideal gas law constant. T is our temperature. And natural log of Q, where remember Q is our reaction quotient. It is at any given moment in the progress of the reaction, not necessarily at equilibrium. It can be at equilibrium, but not necessarily. Okay. Remember, at equilibrium, delta G equals 0. So we could simply rearrange this equation right here, saying at equilibrium, we're just simply going to say delta G equals negative RT ln K. Because remember, K is at equilibrium, where Q is at any given point during the reaction, although it could also indicate equilibrium. So here's just an example. Calculate the delta G of the reaction for these conditions. They're giving you pressures, and they're telling you it's non-standard conditions. Okay, they're giving you delta G naught. Most of the time for these non-standard condition problems, you will be given delta G. Delta G naught. And you will be given a temperature. So what are we going to do here? We're going to solve for Q, because remember, law of mass action, products over reactants. So in this case, we're given pressure, so we can just use that. It's the pressure of the NO2 squared, because we can't forget the coefficient, divided by the pressure of the NO, also squared, because we can't forget the coefficient, times the pressure of the oxygen gas. No power there because there's no coefficient in front of the O2. Once you plug and chug and do the math, you will find that Q is 4.00 times 10 to the 3. No units, they all cancel out. All those ATMs will have canceled out. Once I have Q and I'm given delta G naught, I can simply just plug and chug. It becomes very easy. I plug in my delta G naught, my ideal gas law, my temperature, which has conveniently already been converted for you into Kelvin, and then natural log of Q. I just solved for Q, so I got to take my natural log of Q. I put all that in, I plug and chug, and I find delta G, the reaction, to be negative 50.7 kilojoules, which means in these conditions, this reaction is, in fact, spontaneous. Okay, you can do the same thing here. It's literally the exact same thing, where you have to find Q first. You're given delta G naught of the reaction, and then you're literally just going to plug and chug. So our relationship between delta G naught and K, again, you got to remember, K is at equilibrium. So when delta G equals 0, then, when delta G of the reaction is equal to 0, that means it's at equilibrium. So that means K would also have to equal 0 at equilibrium. So if K is less than 1, delta G is going to be positive. If K is greater than 1, delta G is going to be negative. And when K equals 1, delta G is going to be 0, and it's at equilibrium. By the way, when we say delta G is positive, or actually, let's look at this chart. So when we have a really, really small K, meaning less than 1 with our positive delta G, we can see that it's going to shift towards the reactant side. And that's because delta G's are not spontaneous. It's not a favorable reaction. When I have that negative delta G, that's where I'm going to see that shift towards the product side. And at equilibrium, it's going to be, just like it says, at equilibrium. We're not going to go through this. This, again, is just using your charts, using your values to plug and chug for the delta G's, the delta G naught of formations to figure out your delta G naught of the reaction. Once you have that and you know it's at equilibrium, then you know the natural log of K is going to be the natural log of 1 because they're telling you it's at equilibrium. And or they're saying solve it at equilibrium. What would that K value be for it to be at equilibrium? So is this 1? That's supposed to be a question mark. Wow, that's a really bad question mark. Sorry, I got to recalibrate my pen again. So is K equal to 1, meaning it's at equilibrium, or is it some other value and we need to determine if it's greater than 1, less than 1 to see if we're going to have a positive or negative delta G. So once we rearrange and plug and chug here, you just have to remember that when you have, I'm just going to bring this down, natural log of K, natural log of K. You got to remember your log function rules. We can simply say K is equal to e to the negative power of whatever that number comes out to be. On your calculator, make sure you're using the button that it should, for most of you, if you have a TI, you'll have to hit the second button, and then on my calculator, it's where the natural log button is, and it's yellow and looks like this, okay? So when you have that, you're just literally going to type it into your calculator and solve for it. So again, just kind of, recap and thinking about these two equations, why does the temperature matter with equilibrium? Well, again, if you just think about this in a mathematical way, the higher or small, or the larger or smaller the temperature, the more mathematically things can change to have a positive or negative delta G. So if I were to combine these two equations here and rearrange it, so I had the natural log of K equal to a combining of these two equations, you would see that it is in this y equals mx plus b form. So once you see that straight line equation, you know that it's going to just, be completely temperature dependent. If you were to graph all this, I'm not expecting you to graph it. You can sit down and play with some numbers and graph them if you would like. If you were to graph an actual equation that we did or an actual problem, you would see that you would get this straight line. So our slope here, you can think of this as y equals mx plus b. This is going to be our slope. This is our variable, our x, and b is going to be our intercept. Again, I'm not requiring you to do this, but if you wanted to play around and see it for yourself, do it in Excel. That is it for Chapter 18. Chapter 19 should be posted up here in a day or two.